Welcome to video 2 in this lecture 2 on analog evolvable hardware. So in the last video we looked at custom off-the-shelf devices and how they might be applicable for performing analog evolution. And I think a good summary is that while they can be used, the configuration level is rather high. So it tends to be often at the op-amp level. And hence they're not. There are many functions that we might be able to evolve, which would be difficult to do at the op-amp level. And of course, most of those custom chips weren't off-the-shelf chips weren't designed for evolvable hardware. So what we might like to do is think about devices which have got, let's call them lower level components, so at the transistor level rather than at the op-amp level. And there's a couple of examples here of transistor circuits and how we might have devices such as these to help us perform evolvable hardware in the analog domain. So if we don't have them readily available to order, then the obvious thing is why not build our own? And so many people have done this, a number of people have done this, and there's a few examples here, and we'll go into some detail about what these devices are. So let's just have an overview of some of these, and then we'll delve a bit deeper into some of these examples. So there was a lot of work done in Japan, where they produced evolvable hardware chips specifically for industrial applications, and we'll see an example of this in video 3 of this series, where they're looking at filter design for mobile phones. There's been quite a lot of work done at NASA JPL, so Jet Propulsion Laboratories in America, where they were looking at designing a chip which would be adaptable for various severe environments, and that's the one we'll have a look at in detail in this video. There's actually been quite a lot of work done at York, here at York. So this picture here, towards the bottom right, shows effectively an evolvable motherboard designed for hardware, designed for analog hardware, which was actually done as a fourth-year project a few years ago, and more recently, there's the York Panda chip, which we'll talk about in lecture 3 of this series. So I'll leave you with that for now, but we will come back to that one. There's some work being done in Germany, in the University of Heidelberg, on programmable transistor arrays. And in fact, Martin Tretzfer, who was in the department, was part of that team that designed that chip. And there's been bits and pieces of work done in other parts of the world, so Edinburgh, Brazil, etc., etc. So quite a lot of people have actually looked at this problem and thought, yeah, actually the best thing to do is to design our own chip. So let's have an example of a custom device, and this one, as I promised, is actually done at JPL at NASA in the States. So first of all, what do we want? Well, we want evolutionary-oriented devices which we can program many times. So we don't want devices where we're blowing fuses to program the device, as in the old digital programmable devices, but we want a device where we can program, or evolution can keep downloading bit patterns to reprogram the device. It's useful if we can actually understand what's inside. So what I mean by that is once evolution has come up with a configuration, it's quite useful to be able to effectively read back that configuration and turn that into a circuit diagram, if you like. So actually we know what the circuit is that evolution has come up with. And we want flexibility in our programmability. So we want to be able to program not just the core elements, but also the connections between those, and maybe the passive components between them, etc., etc. So flexible programmability. So an example of this is the JPL programmable transistor array. Here's a picture of one of the versions here on the right hand side. Okay, so this is, as you can see, it's programmable at the transistor level. So in this particular case, we've got 2, 4, 6, 8 transistors in a cell, which we can program. And they were using it for experiments to to evolve both analog and digital circuits. So even though we're focused in this lecture more on analog, and indeed it's working at the transistor level, you can in fact design digital as well. In fact, digital is just analog driven hard, so it's just switching between the two states and ignoring the if you like, the slopes of the transistor characteristics in between. And what you'll see on this device is, as well as lots of transistors, there are lots of switches. So all these S's are switches, and actually this is the thing that the evolutionary program that came up with circuits for this, so that's the thing it was playing with mostly, is actually whether these switches should be open or closed. So you can imagine it's a binary bit pattern to do this, and there's a reference here to some of the work, but it's also included at the end of this video. Okay, so why did NASA want to do this? Here's a simple example of one of the reasons, the work that NASA were doing. And so it was, as we can all imagine, NASA have devices which have to go into extreme environments, and the most obvious one being space, where the temperature operational range for devices has to be very large. And the problem with standard semiconductor devices is if we change the temperatures outside the comfort zone, if you like, the around about room temperature, then the characteristics of our transistors change. So this is a simple graph showing IDS current against VGS voltage. Okay, and so room temperature is around here. So this is the kind of the standard sort of characteristics we might imagine that we get from a transistor. But what you'll see here is if you knock the temperature of the transistor down to -30, or if you move it up to +200, the characteristics change radically. And you can imagine the circuit operation with the transistor that's changing its characteristics like this is going to be pretty severe. It's going to show quite big changes in how it's working. So what NASA wanted to do is they wanted to design this circuit based around transistors, as we've seen, but actually apply evolution to it to if the functionality changes, then bring it back. So this rather simplistic equation suggests that at a particular temperature, with a small variation of temperature around there, and a given circuit configuration is performing function F. If, however, the temperature changes to temperature T2, which I think we should assume is somewhat greater than delta T1, with some variation, the same circuit will not provide the same function. So just simply it's moved from function F to function G, where in fact function G may be no functionality at all. It may actually just stop working completely. And then what they wanted to do was use their device to evolve at that temperature a new circuit which brings back the function. So it brings back from G back to F, which was the original function that they wanted. So that was one of the applications that NASA was really interested in doing. So as it says here, they wanted to use evolvable hardware to preserve or recover the system functionality by reconfiguring the hardware, by reconfiguring that chip that I showed you earlier. Okay. If the device characteristics change with temperature, and we've seen that most transistor circuits are quite likely to change when you increase the temperature or reduce the temperature quite a lot, what they want to do was preserve the function by finding a different circuit solution which explores either altered or modified characteristics of the circuit. So that was what they wanted to do. So the steps for doing these experiments was, first of all, get potentially a human design at room temperature, or it could in fact be an evolved design at room temperature. So it could have been either of those. In some respects, that doesn't matter so much in this particular instance. Okay. They then exposed the chip to a variation in temperatures, a fairly large range of temperatures that it was working at, and actually observed the response, which generally decayed because of the reasons we know with the transistor. And then they wanted to apply their evolutionary loop on their evolutionary hardware chip to get the circuit solution back up functionality, or at least enough that it would still work as required. So this was their setup. It's quite a complicated setup bench. So figure A here at the top left, this part here, okay, is a pictorial version of the experimental setup with a heat pump And the chip under test is here. So the chip under test is just there. And then there's a ceramic cover on the top with a hole, and the heat can come down from this torch up here and controlled by a PID controller to set the temperature and get it to that. And obviously there's lots of other variable things to do with heights and things here that they can do. Okay, so then this is a picture of the actual chip here. So you can see the chip in the middle, with effectively the top of the chip taken off, so that actually the packaging taken off, so they could actually get to the chip and to there. And there's thermocouples attached to it to make sure the temperature is correct. This picture here is actually the apparatus. So this is if you like, a cartoon of it, and this is the actual torch and the chip under test, and the bottom bit there that they can adjust up and down to do that. Okay, and then finally D is a photo of one of the chips heated up. So you can see there that the actual chip there in the middle is bright red as it's been heated up. So this was the experimental setup they used for when for doing these experiments. So this is a design. So the chip I showed you before, you can see we've got transistors. We've got resistors in there, so some of this is resistive links between the transistors, which can be switched, as we know, in or out of the system. So this is at room temperature, okay, where we've got two inputs, and the output is there on this particular device. Okay, and the temperature was swept between minus almost 200 degrees centigrade up to almost 250 degrees centigrade. And evolution was then applied to try and get the functionality back. So in this particular example, when it got down to code, this shows some of the changes in the circuit that were going on to make it back to operational. And over here, this is at +2, nearly 250. And again, you'll see changes that are required to get the functionality back. I'll show an example in a minute of what the circuits look like. Okay, so evolution did automatically find circuit solutions that recovered the lost functionality. So this was all done through evolution. So it wasn't, once the original design was made, so once this one was made, if it was done by hand, everything else was done autonomously by evolution. So what they found was that evolution can recover the functionality of circuits affected by either faults. So even though they were looking at temperature, you could also imagine actually a fault in the system. So one of the transistors breaks or overheats or stops working properly. Okay, to find new circuits, either by bypassing the fault or even by using the damaged component, but maybe in a different configuration. And as we've seen, that they were sweeping it between something like -200 and +250, and maybe even up to 300 to demonstrate the functionality. So here's an actual scope output of the design. So this in fact is a NOR gate. So remember, we're using the transistors, but the transistors are configured as a NOR gate. So this is at room temperature, and you'll see there are two inputs here, input 1, input 2, and the bottom line is the output. So the bottom line is the one that we want to focus on. The top two lines are the same in each instance. So in the first example, they've taken it to 236 degrees centigrade. Okay, and what you'll see is the output with the same input pattern, the output is pretty much degraded down to nothing. It would be difficult to identify what sort of gate that was, what sort of output that was. They then applied evolution to their chip, and what we now find is at that same temperature, approximately the same temperature, slightly more in fact, what we get is a waveform which clearly is not perfect, but it does actually provide, if you compare that circuit on the right with the output on the left, what you'll find is that the output is performing a slightly degraded, but is a NOR gate function. So it is providing a NOR gate function. There is a little bit more noise in places here, but actually it's a pretty good recovery, and it's a pretty extreme temperature range. So that was a nice result, showing that through autonomous evolution, you could recover the functionality. So here's a couple of papers. Both of these papers, in fact, are by the NASA guys. So they're the ones that designed the chip I just talked about. If you're interested to see a bit more detail, there's quite a lot more detail in these papers. So if you're interested, then I would refer you to these papers. So just as a couple of questions for you before we get to video 3 for lecture 2. Okay, so we've seen that actually, if we design our own chips, then evolvable hardware on analog is possible. So what type of applications do you think we might use it for? What applications do you think where evolvable hardware would be really good? Okay, we've seen one, so try and think of some others. Okay, and think about technology and how technology is changing in the future and how that might make evolvable hardware quite useful as future technology comes forward. Thanks very much for that. And there'll be one more lecture, one more video for lecture 2.